We'll now discuss a model for a vibrating string. So in the last video we derived the wave equation using a vibrating string as motivation, but we were kind of vague about it, didn't list our assumptions very clearly, and so we'll now try to be more precise, list our assumptions, and hopefully end up with a more rigorous and convincing derivation. So we begin by playing the same game we did last time, where we take a string, we stretch it out tightly between the two of us, and put a little wiggle in it. So we've got a little wave going down this string. Now let's focus on a tiny segment of this string, sort of like we did last time, but an even tinier, little tiny segment. And let's zoom in very close on that tiny segment. Here it is, tiny segment of string. I'll also put in the equilibrium position for the string, say down here somewhere. There it is. Suppose that we color in a little spot on the string while it's sitting in the equilibrium position. Now we wiggle the string and we watch where that little spot goes. Let me ask you, do you think that it goes to a point which is directly above where it started? Probably not. And the reason for that is, as you wiggle the string, it will stretch. And so you'll see some horizontal displacement of the points on the string from where they were when they were in equilibrium. So you'd probably see it end up somewhere like over here, for instance. Now this is a horizontal displacement that we would have to take into account. And so we don't want to do that. It makes things more complicated. The derivation with this displacement taken into account is done in some textbooks. And so you could look it up if you wanted to, but we're going to ignore that for now. So let me get rid of those dots. Now I told you we'd keep track of our assumptions, so let me keep that promise. Let's make a little list of all the assumptions that we make as we go. So the one we just made is that the motion of the string is strictly vertical. No horizontal displacement at all. Our next assumption is one that you're going to be aware of if you have ever gone walking in the woods and you walk through some brush and you push a tree branch aside and then you let go of it and it snaps back and hits the person behind you. The reason it does that is because the tree branch is resisting bending. If we were to take this string and we were to replace it with some other material, like say a thin piece of metal or something like that, the segment would resist bending. So there would be some forces attempting to straighten it out. They would be acting in a non-tangential direction, trying to straighten out this segment of metal or tree branch or whatever it is. So we're going to assume that we don't have those forces and that there's no resistance to bending. So let's get rid of those arrows and let's add that to our list of assumptions. So no resistance to bending. Another way to say this is to say that the material is perfectly flexible. That's what you'll see in some textbooks, perfectly flexible. There's no resistance to bending, so what forces are acting on this little segment of string? Well, on either side of the segment of string we have the rest of the string, and the rest of the string will be tugging on either end, and this is the force of tension. Now tension, the tugging, can only happen in a direction which is tangent to the end of the string. And so we have these tension forces in directions tangent at either end of the string. Now, let's call the tension vector T, but we need to actually put some other labels on things before we can start writing everything down. So let's say that the left end point of the string sits at the point X, or above the point X, and the right end point of the string sits above the point X plus H. And H obviously is going to be some small quantity, and maybe we'll let it go to 0 eventually, who knows. So we have a very small horizontal distance that this segment is sitting above. So now that we have a label for these things, let's call the magnitude of this tension force the magnitude. So T is not a vector, it's just a magnitude. Let's call it T of x plus h, and it's at some fixed point in time, lowercase t, and the magnitude of this vector will be T of x, comma t. So this T is just some function which says what is the tension, what is the tension force at that particular point on the string. Okay, so we now have at least a beginning, enough ingredients to get started with our analysis. You can probably guess where our analysis will start. It will start with Newton's second law, F equals ma, as it so often does whenever you're trying to analyze a mechanical system. So let's write down F equals ma, and our goal, our objective will be to figure out what each piece of this formula is in terms of the picture that we've drawn here. So let's start with the easiest piece first, and that is the acceleration. Now you may remember from the last video that I used the variable u to denote the position of the string relative to the equilibrium resting level. So it's the vertical displacement of a particular point on the string was u of xt at that point x. Now acceleration is just the second derivative of position with respect to time. So if I want to know how a point on the string is accelerating, I just take the second derivative of that function. And you say, well, wait a second, I'm talking about the segment of string here. And I'll say, okay, well, this segment is really, really tiny. And so if I pick any one particular point on this segment, then that's a pretty good approximation to how the entire segment is accelerating. So we'll go with this a, the acceleration being the second derivative of u with respect to t, as being a good approximation to the acceleration of the full segment. So the next piece of the puzzle is the mass. How can we figure out the mass of this segment? Well, if we have the density, let's say the density is rho, and it's constant. If the density is rho, then the mass of this piece of string is simply the density times the length. So density times length. But the problem is that length is not a nice thing. This is a little curved piece of string. We would have to compute some integral to figure out what its length is, etc. It's not a very good thing. So let's add an assumption that allows us to approximate the length in a way that simplifies our end result. So let's add the assumption that the displacement of the string is small. So small vibrations. So small vibration, displacement is small. And what does this assumption do for us? Well, a small vibration means that the string is very flat. It's not wiggling a whole lot. A large vibration would look like this, right? And that would mean that the length would be very different from the horizontal distance from x to x plus h. A small vibration means that the total length would be something very close to the horizontal distance from x to x plus h. So the assumption that we have only a small vibration means that rho times the length, in other words, the mass of that segment of string, is approximately equal to rho h. We can actually be a little more general. Now, you normally think of density as something which is allowed to vary over an object, not a constant simply equal to mass per unit length. So let's allow the density to vary over the string. So it would be a function, say, rho of x. Now, how would we compute the mass if the density is allowed to vary? Well, we remember that this little segment of string is very small. And so by picking any particular point on the segment, the density at that point will be very close to the density at all the other points around it on the segment. So let's choose one point on the segment to represent the density of the entire segment. And let's make the choice of, say, the left endpoint. So the density at the left endpoint would be rho of x, and that would make approximately the mass of the whole segment equal to rho of x times h. I could choose, say, rho of x plus h to represent, or any other point in between, but rho of x is simply a convenient choice. It's time for the real crux of this argument, and that is to figure out what the forces are that are acting on this little segment of string. So let's look at the tension forces that are tugging on either side of the segment. Specifically, let's zoom in on this tension force on the right-hand side of the segment. So I'll redraw that tension vector here, so it's a little easier to see. Here's the right-hand end of the segment of string. I'll draw in a line which just represents the horizon, so just a horizontal line. And you know that this vector will split into two components. It'll split into a horizontal component and a vertical component. So this is the forces in the horizontal direction, forces in the vertical direction, whose sum is this tension force. Now the magnitude of this tension force is T. And so if we call this angle theta, I can write the magnitude of the horizontal component as T cosine theta, and the magnitude of the vertical component as T sine theta. Okay, I'm going to go a little crazy here. I'm going to go back and I'm going to erase our tension forces that we had here on the string, and I'm going to redraw them with their components. So I have a horizontal component and a vertical component to the tension force on the right hand side, and I have a horizontal component and a vertical component to the tension force on the left hand side. Let's think carefully about this for a second. We've split the forces into components. If we look at the horizontal component only, these horizontal components tug the segment of string left and right, but we've assumed that the motion is strictly vertical. So my question would be, well, what is it that these horizontal components are doing? And the answer is nothing. They need to be canceling one another out. They need to be in equal magnitude in opposite directions. The small vibrations backs up this idea that they have about approximately equal magnitude, because if the string is very flat, then the two horizontal components will be very close to equal. So what we should really be concerned with is only the vertical components. So let me X out these horizontal components, and let's take a closer look at the vertical parts only. Okay, so what are the vertical parts? Well, over here, this guy is at the point X, and the magnitude of the tension vector was T of xt, and the vertical part must be then multiplied by the sine of theta. But now theta is varying from point to point, so let's write theta of x comma t to be precise here. Now on the other hand, this vertical component, the tension vector had a magnitude of T of x plus h comma t, and now multiplying by sine of theta, but now theta will be evaluated at x plus h comma t. So these are the two vertical forces. We're pretty much ready to say what F is now. The horizontal parts cancel one another out, and so the force acting on this segment is just the upward force from this vertical component and the downward force from this vertical component. So let's write down F. Up is positive, so we have T of x plus h comma t times the sine of theta of x plus h comma t minus T of x t sine of theta of x t. Now if we had other external forces, we could then add those in. So we could say plus, let me write that in another color, we could say plus external forces. So we could add those in if we wished to do so right now. Really, the rest of the argument is purely mathematical. We're done analyzing forces and things like that. So let's just combine what we've got above with what we've got below by saying that the force is equal to ma, which is simply rho of x H times UTT. Okay, so this will be the starting point for the rest of the argument. All right, so I've rewritten the equation that we derived in the last slide, and our job now is to work with this equation and try to get it into something more manageable. So the first thing to do is to divide both sides by h. All right, so I'll divide by h, and we'll get rid of the h on the right-hand side. And then you notice that this left-hand side now has the form of a difference quotient in x. I have x plus h, I have x, and I've divided by h. So if I take the limit as h goes to 0, and I just do that with both sides, then I get on the left-hand side the partial derivative with respect to x of t of xt times the sine of theta of xt. And the right-hand side didn't involve any h's, and so that's still just rho of x utt. What's the meaning of taking the limit as h goes to 0? Well, h was the horizontal length of our segment. So what we've done here is we've allowed the size of the segment to tend to 0. This equation is a little better, but it's still not very satisfying because we still have this sine theta term, and it's not quite clear how to deal with that. Really, we want everything in terms of u. We want a differential equation in u. So let me give you a little argument as to how to get rid of this sine theta. Let's begin the argument by drawing a little segment of the string again. And let's draw the tangent line to that segment at a point. So there it is, tangent line to the segment of string. And remember that the axes that we have are u and x. And that means that the slope of this tangent line right here is actually equal to ux. On the other hand, we had a tension vector that we drew, and that tension vector was tangent to the string. And the tension vector was split into two components in terms of this angle theta that we have. There was the horizontal and the vertical component. Now, since the tension vector is tangent, that means that the slope of the line, the slope of the tangent line, can be given as a ratio, the rise over the run. And so the slope of this pink line is the same as the length of this divided by the length of this, which is actually the sine of theta divided by the cosine of theta. In other words, the tangent. Now remember, assumption number 3 was that our vibrations were very small. And if our vibrations are very small, then this little segment is very close to flat. And so the tangent, in other words, the sine of theta over the cosine of theta, is very close to being equal to simply the sine of theta, because the cosine of theta is very close to 1. So sine of theta is closely approximated by ux under assumption number 3, that the vibrations are very small. Well, this means that we can now take this equation that we have with this undesirable sine of theta and replace that sine of theta with simply ux. So this equation then becomes, by assumption number 3, we're using that in a critical way, the partial derivative of the tension T of xt times ux is equal to rho of x utt. This is essentially the general equation for a vibrating string. So this is the equation for a vibrating string that we aimed to derive in the first place. Now, we could have made this equation a little bit more general, and you could go back through and you can look at ways to add some generality. For instance, you could add in external forces. I made a note in the last slide where that would be done. So you could come back to this equation again and add in more terms. What I'd really like to do is the opposite. I'd like to make some assumptions which make this equation even simpler. So let me actually just box off this little argument that we did here just to keep it separate from what we're writing here. Let's add an assumption. Let's add, well, two assumptions. Let's assume that t is constant. T of xt is equal to just simply t, which is constant. And let's also assume that rho is also constant. Now this assumption that t is constant is often called the assumption that the string is perfectly elastic. Meaning, as you stretch it, its tension forces do not increase. So it has perfect elasticity. The assumption that rho is constant is just a uniform density. With these assumptions, the equation for a vibrating string becomes a very familiar equation, the wave equation. So let's just write that down, just so we conclude our argument. T is constant. Therefore, the t can come out of this partial derivative. The left-hand side becomes t uxx. Partial derivative with respect to x of ux is uxx. And that is equal to rho times utt. This, of course, can be rewritten as utt equals c squared uxx, the familiar version of the wave equation that we saw before, where c is the square root of t divided by rho. Now, rho is never zero. It's a density. It can't be zero, and so I'm okay dividing by it. And both t and rho are positive quantities, so it's okay to take their square root. So the wave equation is now a consequence of all of this business that we've been doing in this, and hopefully all of the assumptions that we made in order to construct our model, to derive the equation for a vibrating string, and eventually to end up at the wave equation. Hopefully all those assumptions have been fairly clear and transparent.